Hello students, welcome to the course on Basic Electronics Engineering and the course code is EC101. This is the course for BTech second semester EC students and first semester CSE students. Myself, Dr. Shurojit Boshak, Assistant Professor of EC Department, Guru Nanak Institute of Technology, Kolkata. And this is my official email address. Today, we are going to start lecture number 2 from the module 4, that is field effect transistors. In the last class, we have completed JFET, that is junction field effect transistors, which includes its construction, comparison with BJT, construction, working principle, symbol, JFET characteristics, that is drain characteristics and transfer characteristics, in addition with the application of JFET. Now today, our topic is metal oxide semiconductor field effect transistor, which is abbreviated as Mosfet. And the lesson objectives of this topic is to learn principle of operation, construction, and characteristics of various electronic devices. And second lesson objective is to know about different applications of these devices. And this topic is mapped with CO number 2 and CO number 3. So let us start lecture number 2 from the fourth module, that is field effect transistors, with the topic of Mosfet. So Mosfet or metal oxide semiconductor field effect transistor, it is also known as insulated gate field effect transistor, is an important member of FET family, which has a very important advantage of having large input impedance compared to that of JFET. The input impedance may be as high as 100 of mega ohm, which is due to the fact that the metal contact of the gate is separated from the semiconductor channel by silicon dioxide, which is an insulating layer. There are two different modes of MOSFET, which are classified from the constructional and application points of view. Number one is the enhancement MOSFET and second is the depletion type MOSFETs. Again, each of these two types of MOSFETs may be classified as N channel and P channel. So let us start the N channel enhancement type MOSFET. This is the structure of an N channel enhancement type MOSFET, and this figure are the symbols of N channel and P channel enhancement type MOSFET. So first start the physical structure of an N channel enhancement MOSFET. The structure of N channel enhancement MOSFET has two highly doped N plus regions are diffused in a lightly doped P-type silicon substrate. The terminals, which are aluminum or metal contact for these n plus regions are called source and drain terminal, and they are separated a thin insulating layer of silicon dioxide or SiO2. A thickness is grown over the surface of silicon substrate and patterns are formed into the oxide layer by masking and photolithography so that source and drain contacts can be made. A gate metal is deposited on silicon dioxide layer to cover the whole channel region, and a contact to this metal over the channel area is the gate terminal. So a MOS structure basically formed by the gate metal along with the insulating silicon dioxide layer and the semiconductor channel. The channel and gate act like two parallel plate capacitors separated by a dielectric or silicon dioxide layer. This layer is responsible for high input impedance for Mosfet, and also the reason for the name insulated gate field effect transistor, as SiO2 is an insulating layer. And this is the symbolic diagram of N-channel enhancement type MOSFET, and this is the symbolic diagram for P-channel enhancement type MOSFET. See the current substrate which is connected to the source, the direction is reversed for N channel and P channel. Now go for the principle of operation. Principle of operation of N channel enhancement MOSFET. If a positive voltage is applied between source and drain, keeping the substrate at ground potential, no current will flow through the channel between the source and drain, as the channel is p-type between two n plus diffused island. Now, if a positive voltage is applied at a gate, assuming the substrate at zero potential, the positive charge on the gate induce equal amount of negative charges on the substrate between source and drain. These negative charges of electrons, which are minority carriers in the p-type substrate, form an inversion layer between the two diffused n layers. See, this is the inversion layer. The positive gate voltage will establish a transverse electric field through the oxide, which will end on induced negative charge, that is inversion layer on the semiconductor side. See here, with the increase of positive gate voltage, the amount of induced negative charge increases, thus extending the inversion layer between two n plus diffused regions. The accumulation of electrons between the two n plus diffused regions forms a conducting channel, and current flows through the induced channel from the source to the drain. The magnitude of the drain current increases with the increase of positive gate voltage due to more and more accumulation of electron in the top of p-type substrate. Since the drain current is enhanced by the positive gate voltage, the name enhancement is appropriate for the N-channel Mosfet. Now, similar to JFET, Mosfet also have two characteristics. One is drain characteristics and other is transfer characteristics. So this is the drain characteristics of an N-channel enhancement MOSFET. Where we see that the y-axis is the drain current ID in milliampere and x-axis is the VDS, that is drain to source voltage in volt, and for a different values of VGS. So this is the drain characteristics. And next is the transfer characteristics. Transfer characteristics indicates that for VGS less than equal to 0, a very low drain current of the order of a few nanoampere, see here in this region, of the order of a few nanoampere flows, which is designated as this IDSS. When VGS is made positive and allowed to increase, the current ID increases very slowly at first till VGS reaches a threshold value called gate source threshold voltage. This threshold voltage, or which is called say VTH, at which ID attains a value say 10 microampere. The drain current at any point in the transfer characteristics is given by the relation ID equal to IDSS plus K into VGS minus VGST whole square, where K is a constant whose value depends on the type of MOSFET. Its value can be determined from the specification sheet if ID on and corresponding VGS are substituted in the above equation. So this is all about enhancement type MOSFET. Next is the depletion type MOSFET. So this is N-channel depletion type MOSFET. The structure and construction of N-channel depletion MOSFET is similar to that of an N-channel enhancement type MOSFET, except that here see a lightly doped N-channel is diffused between source and drain regions, see in the figure. Now, see the operation. After we applying biasing, an appreciable drain current IDSS flows even VGS equal to 0 as the lightly doped N layer between the source and drain acts as a channel. If the gate voltage is negative with respect to source, induced positive charge below the gate dielectric or SiO2 layer, this positive charge, see, which is depleted the doped N layer in the channel and make the channel less conductive. So the accumulation of positive charges in the channel restricts the flow of electrons between the source and drain, and hence the drain current decreases as VGS is made more and more negative. An effective depletion of majority carriers, that is electrons in the channel, due to negative gate voltage with respect to source takes place, for which this Mosfet is designated as depletion type Mosfet. The channel region near the drain is more depleted than near the source. See here, source is less depleted and just near the drain it is more depleted. The reason is that the voltage, due to the voltage drop caused by the drain current. This situation is similar to that of pinch off occurring at the drain end of the channel of a JFET. A depletion type MOSFET can exhibit enhancement mode if VGS is made positive, so that the negative charges are induced in the channel through the SiO2 layer of the gate capacitor. The drain current increases with the increase of positive gate voltage, and the drain characteristics shifts upward. These characteristics are similar to the drain characteristics of N-channel enhancement type MOSFET. And this type of MOSFET exhibits depletion mode for negative gate voltage and enhancement mode for positive gate voltage. Now see the drain characteristics. See, for upper, that is the for positive voltage of VGS, this operated like an enhancement mode, same. But for negative voltage, it operated basically depletion type mode, same as depletion type mode. And the transfer characteristics, see, for both cases, in the case of negative, here we get a sufficient amount of current. So, and obviously in the positive case, surely we get a large amount of drain current. So in the positive case, this behavior is like same as enhancement mode. And in the negative case, this behavior is like a depletion type mode. And this intermediate point is called IDSS. And this is the, so in channel external substrate, N channel and P channel, depletion type MOSFET with external substrate, and with the substrate is internal, that is, it is connected to the source. And remember the arrow correction. For N channel substrate, the arrow is like an inside. And for P channel, the arrow is in outside. So this is about enhancement type MOSFET and depletion type MOSFET. So the main difference between enhancement and depletion type MOSFET is in case of between two N plus island, or in case of between source and drain, for enhancement type MOSFET, there is a channel which is induced channel is present. Physically there is no channel, but the channel is induced. But in case of depletion type MOSFET, a low amount of already channel is present, which is called basically a diffuse channel between two N plus regions, or better to say between two source, between source and drain. So that is the main difference between enhancement type MOSFET and depletion type MOSFET. Next, I come to the comparison of MOSFET and JFET. The channel conductivity of both modes of MOSFET is basically controlled by a transverse electric field applied from gate to channel through the gate dielectric or SiO2 layer. In JFET, the conductivity of the channel is controlled by a transverse field across the reverse bias PN junction. Second is the gate leakage current in a MOSFET is of the order of picoampere, while that in a JFET is of the order of nanoampere. That means the MOSFET have much higher input impedance than JFET. Third is the drain characteristics of MOSFET are less flat than those of JFET. MOSFETs have lower drain resistance than JFET, typically 0.1 to 1 mega ohm. The most important is the JFET can operate only in the depletion mode, while MOSFET can operate in both depletion and enhancement mode. Next is the fabrication steps of MOSFETs are simpler than those of JFETs. MOSFETs are sensitive to excess load voltage. These devices get damaged due to mishandling. Next is the MOSFETs have zero offset voltage. The source and drain terminals can be integrated because of the symmetrical nature of the device. Therefore, MOSFETs are useful in analog signal switching. Next is the MOSFETs find more useful and wider application in digital VLSI circuits than JFET. Special purpose digital CMOS circuits are available for low voltage and current requirement and low power dissipation. So these are the main comparisons between JFET and MOSFET. Again, there are only 3 leads, there are only 4 leads including substrate. gate current is more, and again gate current is less. So that's all about MOSFET. One important question of this portion is the item number 4. That is, there may be asked to explain that why JFET can operate only in depletion mode, while MOSFET can operate in both depletion and enhancement mode. The reason I already discussed. Okay, so let us stop here. I am now ending the today's session. Thank you so much.